Well, thanks for the invite. Let me start this one off. Okay, this presentation deals with closed loop geothermal systems. And if we look at the components of a geothermal heating system, we have the emitters, such as the radiators and underfloor heating systems, the heat pump itself, and control systems which ensure the system works efficiently. Now, if I go to a trade exhibition, these three items are well represented on numerous stands. And that's not the case for the ground collector. In all honesty, it is rather a challenge to get that excited about a piece of plastic tube. However, if that plastic tube is not installed correctly, then it doesn't matter how good the other components are or how much you tweak them, the system will not work properly. Furthermore, if the ground collector has defects, it may take some time to determine that the problem in the heating system is actually down to the ground collector itself. By then, access to the ground collector could be difficult if it's been covered by a building or car park. So it's important to get it right. So this presentation will hopefully give some insight into how we ensure that the ground collector does not let the side down. Now, I've been invited by Geological Survey of Northern Ireland to this webinar, so this is their plug. We have at our disposal the most comprehensive geological records on the planet. Records go back to 1835, and we have some 155,000 borehole records on the Geological Survey database. Historical records of the underlying geological strata and the likely depth of the water table are vital for preparing for the drilling project. I cannot overemphasize the importance of the data and also its interpretation by geologists. Our geologists will use the database to prepare a desk study for the project in line with the requirements of the design of the heating system. So let's look at what the desk study will contain. Well, obviously, it's going to have information on the underlying geology. I need to know the total amount of drilling meters required, how many boreholes we intend to drill, how deep each borehole should be, the position of each borehole, the drilling techniques required to cope with the geology and also the depth, bearing in mind that there may be multiple drilling techniques required. There are other considerations, possible artesian water, which will require to be managed, possibility of intercepting coal measures. If that's likely, then a permit's required from the coal authority in advance of drilling. If you trespass into their workings, they will fine you. In some areas, there are potential legacies from the Second World War bombing raids by the Luftwaffe, and that may require a further investigation into unexploded ordnance. And there are also obvious underground structures which you need to avoid. There are clearly things like utilities and electricity, water, that sort of thing, but there are also specific issues. If I'm drilling in London, I don't want to intercept the Bakerloo line. When mobilizing to a site, I need to take the appropriate equipment. There are standard items such as the drilling rig and tooling. That goes for any drilling project. For geothermal projects, I'm also going to need specialist items such as a loop feeder, grout pump, and loop testing equipment. I may also need an air compressor, drill casing, and a system for handling drilling fluids. So let's look at drilling rigs. Well, they come in all shapes and sizes and must be able to get to the target depth efficiently. This one weighs in at about 9.5 tons and will work efficiently to about 140 meters. This one is much larger. That weighs in at about 36 tons, and that one's good for about 200 meters. As we all know, size isn't everything, and although this rig weighs in at only 16.5 tons, it is very powerful and can drill down to a depth of 340 meters. It also has some special features which I'll go through later. The size of the rig can have access issues on some sites. On this one, the builder almost blocked the rig in by surrounding it with new properties as we installed a large ground collector system. So it's advisable to get the ground source collector in before you start doing the building. Another access issue, we were drilling on a remote island and we required assistance from the army to move the rig onto the site. And they undertook this project as a training exercise. That rig weighs in at 9.5 tons and that Chinook has a lift capacity of 10. So that was a little tight, to say the least. Let's look at drilling tools. So having selected the drilling rig, we now have to choose the appropriate drilling tool itself. And selection is based on the rig, the target depth, and the likely geology from the Geological Survey records. I need to know how much overburden I'm likely to encounter, the underlying rock type, and whether I'm likely to encounter strata which is going to collapse behind the drilling tool. Again, I have a wide range of tools available to me. This one is a drag bit. This is a cutting tool with tungsten carbide edges for drilling through soil, clay, sand, and soft rock, such as sandstone, shales, and mudstones. When the drag bit starts to struggle, then I may consider a PDC bit, and that stands for a polycrystalline diamond cutter. This has industrial diamonds bonded to the steel cutter to scrape and gouge its way through the rock. Another alternative is the tricone rock roller bit, which has tungsten steel carbide teeth, which rotate and self-clean. The tool itself crushes its way through the strata. Now, all of the drilling tools rely on rotation and force to drill through the strata. Now, that's the down-the-hole hammer, which has an internal piston which moves the tool up and down rapidly using compressed air. The tool, in addition to rotation, moves up and down to pulverize the rock into a dust for penetration. And you can see there are no sharp teeth on that tool, just very hard carbide buttons. And many of you will have used a Black & Decker type hand drill at home. If you're drilling through, for example, a wall, you would have noticed that the drill bit gets hot due to friction. Now, for a drill borehole, we may be drilling for many hours and we need to flush the borehole to cool down the tool. We have a number of options. We can use just air. We can use air and water, which forms a mist. We can use air and a chemical, which forms a foam. We can use water on its own, or a proprietary drilling fluid, often referred to as a drilling mud. And in addition to cooling the tool, we also need to bring to the surface the rock we have drilled through to create the void. So the borehole flushing not only cools the tool, it also lifts the cuttings to the surface. Now, there is a danger when drilling through unconsolidated strata, such as sands, gravels, and fractured rock, that the hole will close in behind the drilling tool. If that is likely, it's essential that you support the borehole as you drill to prevent losing the drilling tool itself. Now, drilling fluids can be used to stabilize the inside of the borehole to prevent borehole collapse by lining the borehole with a thin layer of mud to bind together the loose material. Drilling fluid management is a highly sophisticated technology, and there are a vast number of products on the market which are available. The use of mud does, however, create an issue, as the mud which returns to the surface will include the cuttings that have been drilled through to create the void. The returning fluid is a mixture of mud, rock, soil, and sand. The flow rate of the mud to the drilling tool is high, and mud is an expensive product. So we use a mud recycling system to separate the cuttings from the mud to enable the mud to be reused. Now, this is a mud recycling system which passes the return mud over a vibrating screen. The mud falls through the screen and into the tank below, whilst the large particles are rejected onto the chute. Finer particles are then pumped from the tank into a cyclone, which separates the mud from the finer particles by centrifugal force. Now, we use a lot of mud when we're drilling, and this unit can process 35 litres a second. When we're drilling through unconsolidated strata, we can use mud as an alternative. We may use a supporting borehole using a steel casing itself. This is usually a preferred option when drilling through the initial stage of a borehole in the first 60 meters. And you can see here the drill rod at the bottom, and surrounding that is the larger steel casing. Now, the rig shown previously, which could drill down to 340 meters, can simultaneously drill and case the borehole. The drill rod and tooling rotate in a clockwise direction, and the casing rotates anti-clockwise. And this makes for some very complicated plumbing at the drill head. So when we have drilled to the required depth, we now have to install the heat collector, which is also known as the loop. Loops are tested at the point of production. However, their performance will be adversely affected if they subsequently sustain damage as perforations, which will leak, or kinks, which will impede fluid flow. So extreme care is required during transportation, storage, and installation to prevent loop damage. Prior to installation, the borehole should be inspected. To the borehole, the loop should be inspected and rejected if there is damage which exceeds 10% of the wall thickness. Loops are heavy, and we avoid all manual handling during installation. Firstly, we transfer the loop onto a rotating loop reel. Then we introduce the loop into the borehole using a hydraulically driven loop feeder, which avoids contact with any sharp items during the installation process. Very often we're installing the loop into groundwater. We fill the loop with water to avoid buoyancy. Now, you may have noticed there are 3 pipes on that photo, and we'll come back to that later. So having installed the loop to the required depth, we then need to ensure there is intimate contact between the loop and the surrounding strata for efficient heat transfer. For this, we use a pressure grouting machine, which is similar to a concrete pump. It mixes the grout powder with water and injects it under pressure using an Archimedean screw. In order to ensure the entire borehole is grouted, we inject the grout from the bottom using a 3rd pipe, which was the tremie pipe we saw earlier. And you can see the 2 pipes for the loop and the 3rd tremie pipe, which is there. We continue to pressure inject grout until the grout comes to the surface. That way we know we've filled all the voids. The grout will enter any voids created during the drilling, and you always use more grout than the theoretical amount. So now we've grouted the loop in place, we have to confirm the loop is fit for purpose. Now, I've been involved with the Ground Source Heat Pump Association regarding loop testing. We have looked at standards from numerous countries. There is a draft European standard being worked currently, but that simply states the loop should be tested for pressure and flow, and that the results should be recorded. This is clearly unsatisfactory. So the Ground Source Heat Pump Association have looked at numerous standards and have actually produced their own vertical borehole standard, which was issued in March this year, which includes a section on loop testing. Now, a loop is made of highly durable polyethylene and should have a working life of 60 years and quite probably longer. If it leaks, not only will it adversely affect the performance of the heating system, it will also release potentially polluting thermal transfer fluid into the environment. It is essential, therefore, that the loop does not leak, and we test loop integrity by using a pressure test. Now, pressure testing is not straightforward. Any flexible material, certainly polyethylene, is not straightforward, as the material is subject to something called viscoelastic stress, or creep. Effectively, it expands when pressurized. Now, polyethylene pipework has been extensively used in the water supply industry for decades and is tested for leaks in accordance with British standard BS EN 805, which allows for creep. And we use that test for the leak testing of loops. That's the pressure profile of BS EN 805. It's a test that can be performed in about 2 hours. The loop is pressurized for 10 minutes to 12 bar. The pressure is then allowed to decay for 1 hour, followed by a sudden pressure drop of 1.2 bar. The loop then rebounds back, and you measure the pressure for the next 20 minutes. And if that pressure doesn't decrease by more than 0.1 of a bar, then the loop is considered to be intact. And there are times when we may extend that pressure phase between point A and point C. We can extend that for several hours if required by the designer. The Ground Source Heat Pump Association Vertical Borehole Standard requires the loop to be tested for flow at the design flow in both directions. There have been occasions previously where an obstruction has caused minimal resistance in one direction and then has opened like an umbrella when the flow has been reversed. That is why we test in both directions under the guidance. So on completion of successful testing, the loop should be sealed to prevent entry of debris. Now, I've been working on apparatus which will undertake the pressure and flow test as a fully automated sequential operation using pre-treated water and also confirming the borehole location by global positioning satellites. The prototype has been built with assistance from Glyndŵr University and has been supported by a grant from the Welsh Government. The system is now being installed in a towable trailer for use as field testing equipment, and that will make loop testing easier for the operatives and will be more accurate and consistent in the future. The final task for the driller on a project is to complete a drilling log, confirming details of the borehole. This will include the depth profile and also a description of the strata that has been drilled through. It will also include loop insulation details. This one shows Symmetrex drilling, which is a case drilling method for the first 29 meters through soil, sand, clay, and heavily fractured mudstones, which were clearly unstable ground. There was then open hole drilling for the remainder of the borehole, which went down to 200 meters. The loop itself was installed to 196 meters, and there was 6,250 kilos of grout used to grout the borehole up. The log has a 6-figure grid reference for identification, and we voluntarily submit our logs to the Geological Survey to be put on their database. So there we are, the finished product. 2 pipes sticking out of the ground, not that spectacular, but very challenging.